Chapter 14 is all about chemical kinetics, and that's basically the speeds at which reactions take place, and we call this the reaction rate. Chemical kinetics is basically the study of reaction rates within different chemical reactions. And we'll see something called the rate law. And with many laws, we have theories. And so the theory that we'll study at the very end is called mechanisms. And those are the kind of like the step-by-step view of what's happening between going from reactants to products. Some of the factors that impact what the speed of a reaction is the state of the reactants, whether they're solid, liquid, or gas, the concentration of the reactants, the temperature of the reaction, and whether or not there is a catalyst present. And so those are the things we're going to study kind of in that order in this chapter. So we're going to dive into each one briefly, each of those factors that we just talked about. Firstly, the physical state of the reactants, and this kind of goes with kinetic molecular theory that we learned in the gas chapter. Basically, it says that the more readily that reactants collide, the faster that they react. Right, so if every molecule is just bumping around until it eventually bumps into another reactant or another chemical, then it's going to, once they interact and collide together, if they do that with enough energy, then the reaction will happen. When we have homogeneous reactions, so whether all of the reactants are in the gas phase or liquid phase, these tend to be faster. Heterogeneous reactions, specifically that involve solids, are slower, and that is because solids don't move, and so they're dependent on something like a gas or a liquid adhering to the surface. And so this actually speeds up when we have a high surface area. So if the surface area of the reactants is increased. So basically if we have like something that's a fine powder is going to react a lot faster than if we have something that's in a pellet form or a tablet form. And you've seen this, right? If I wanted to, like the process of dissolving sugar into water, if I wanted it to dissolve faster, something like powdered sugar would do so a lot easier than if I had like a sugar cube. Another factor that we'll see impacts reactant rate is the concentration of the reactants. And this is similar to what we saw earlier, that the more often we have reactions, the more... Another factor is the reactant concentrations, and this goes along the lines of what we said earlier. The more often we're having collisions, the more often we're going to have reactions that occur. So when we increase the reactant concentration, we generally see the reactant rate, or the reaction rate. And that's just because, we have more molecules available to react, so there's more likelihood that we'll have a reaction occurring due to more collisions. So here we can see still wool, so this is iron, reacting with oxygen, just regular oxygen in the air, and there's a reaction occurring. But if we put that same still wool in pure oxygen in this flask, you can see that the reaction is just happening a lot more vigorously, so a lot faster. The next factor we're going to talk about is temperature. In general, reaction rate increases as we have a higher temperature. You guys know that when we have a higher temperature, then the kinetic energy is higher, meaning that there's more molecules moving faster. So that's going to increase the number of collisions, as well as how hard those collisions are gonna be. So we're gonna have higher energy with each collision, making it more likely for a reaction to go to succession. The next one is catalysts. So catalysts impact the rate of the reaction without being consumed in the reaction. So basically they go into the reaction, help it out, and then they pop back out the other side. They can change the mechanism or the pathway that the reaction takes place to make it easier to happen, so happening under lower energy. And catalysts are really important for many biological reactions in your body and on the earth. So we call those catalyst enzymes. So getting into what reaction rate actually is, a rate is a change in anything over a given amount of time. For reaction rate, we're talking about changing in a concentration over a given amount of time. So this delta means change, and then these brackets mean change in concentration. So if I had a solution or a concentration of, let's say, sodium chloride, I would write sodium, like concentration of sodium chloride is like 0.1 molar, just for an example of how we use that the brackets. And then in the denominator is the change in time. And usually that's in seconds, but it will depend on, how fast the reaction is going, whether you use different units for time. We have different types of rates. We have an average rate, instantaneous rate, and initial rate. Initial rate is an instantaneous rate, but at the initial, so at t equals 0, at the very beginning of a reaction. So let's practice. We have a reaction here where we have A reacting to become B. And here we have 1 mole of A, 0 moles of B. After 20 seconds, we have 0.54 moles of A and 0.46 moles of B. And after 40 seconds, there's 0.3 moles of A and 0.7 moles of B. So notice that in all of these cases, if you add up the moles of the reactants and the products, you have a total of 1 mole. So that's just showing us that mass is conserved in this case. All right, so in this question, we want to find the average rate at which A disappears over the time from 0 to 20 seconds. So how we're going to do that is we're going to say the reaction rate, the average one, we'll do a little line over, is equal to the change in concentration of A over the change in time. And we're talking about a reactant disappearing, so we're going to put a negative out front. And in general, when we have reactants, when we talk about the rate of a reactant disappearing, we're going to have a negative out front, and a product appearing will have a positive out front. And that's because rates of reactions are always positive numbers. So what we'll do here is we'll say, okay, from time period 20 to 40, so we're going to end with 40 seconds and start with 20 seconds, because we always do final minus initial. And at 40 seconds, we have 0.3 moles of A. And at 20 seconds, we have 0.54 moles of A. So when we do that calculation, we do 0.3 minus 0.54, and then we'll take that number and divide by the 20-second interval, and we get 1.2 times 10 to the negative 2 mole per second. And if we assume that this is in 1 liter, then we could say it's that many molar per second. All right, you can see though that in this first case, the reaction is happening a lot faster in the first 20 seconds because we have a bigger difference between the reduction of A from time 0 to time 20 than we do in A between time 20 to time 40. In this case, our delta A is, or change in concentration of A, is 0.46 moles. And in the case between 20 to 40 seconds, that change in concentration is 0.24 moles. So we can see it slows down over time. So it says if the experiment runs for 60 seconds, 0.16 moles of A remain. Which of the following statements is or are true? So it says after 60 seconds, there are 0.84 moles of B in the flask. So let's see, if we add up 0.16 moles of A plus 0.84 moles of B, we should get 1 mole total if this is true. So we'll do the math, and yep, we get 1 mole total. So this is a true statement. The decrease in the number of moles from A from 0 seconds to 20 seconds is greater than that from 40 seconds to 60 seconds. And yeah, we saw that already. We saw that from 0 to 20 seconds, we had a 0.46 mole decrease, and from 40 to 60 seconds, we'll go from 0.3 moles to 0.16 moles, and so that is a decrease of 0.14 moles. So yeah, that's definitely true as well. And then the average rate for the reaction from 40 to 60 seconds is 0.7 times 10 to the negative 3 molar per second, and so let's just calculate it. We'll do rate equals negative, because it's a reactant disappearing, change in A over change in time. we know that it went from 40 to 60 seconds, so we'll do 60 minus 40, and at 60 there was 0.16 moles, minus at 0.3, or at 40 seconds we had 0.3 moles, and so we'll get 0.14 divided by 20, and yes, that is 7.0 times 10 to the negative third mole per second. So yes, that is correct also. So as we measure reaction rates, we can follow it. We can use either a reactant or a product, as I mentioned. So if we use a reactant, then we're going to say that it's the disappearance. So we're going to have a negative out front. If we're talking about a product, we're going to have a positive out front. So if I was measuring the rate using one of the products here, let's say the alcohol version, as a positive change in the concentration of either HCl or C4H9OH over the change in time. So reactants are negative out front and products are positive out front, and that's because we always have our rate being a positive number. We could plot the data to tell us more information about the rate, because basically what we can do is track the concentration of a reactant or a product over time and determine the slope to tell us the rate. So the slope at the curve at one specific point in time is the instantaneous rate. And when we do that at time equals 0, that's called the initial rate. And this is the one that's actually more important to chemists, and that is because as we saw earlier, the fastest point of the reaction is that initial rate, right? The earlier it is, the faster it is. And so that's kind of like the best point and the easiest point for comparison is just to say the very, very beginning initial rate. So here is some data. We have time here for the x-axis and concentration of the reactant in the y-axis. And this was plotted over time, and we can see these plots over here on this graph. Now we could calculate the average rate of each point by saying, the change in the reactants divided by that time period, and it would give us the average rate like we saw on the last slide. But we could actually approximate the slope at a given point in time to find the instantaneous rate. So you can see here that we have our average rates, and they are decreasing as time goes on, but we can find the initial rate by basically taking a tangential line on the curve. So what you want to do is actually put like a ruler or a piece of paper next to the curve at the time you're interested in. So we're going to do it for the time 300 seconds, and we're going to approximate along the curve. And so we can see okay, at that given point, that slope is approximately what I drew right there. So then what we get to do is, now that we have a line that we approximated that's tangent to our curve at that specific point, is we can use those new points to figure out the slope of the line. So I could take this and I can say, okay, at this point here and this point here, I will use those points to figure out the slope at the time I was interested in here. So let's practice that. We're actually going to first do it at 600. So we're going to find the rate that they did for us here. They found a tangential line at the 0.600. So we can say the rate is a change in our component here. So C4H9Cl over change in time. And so let's pick the points for this guy. I'm going to do it in blue. We'll pick the points. I like to do it on the grid, so we'll do at 800 seconds, and let's actually do it right at this point because it is right at a concentration that's marked and a time. So what we're going to do here then is we're going to say, okay, our two times that we picked were 800 seconds and 600 seconds. and the concentration at 800 seconds, I'm going to approximate to be that looks like maybe like 0.017 molar, and at 600 seconds it looks like it is 0.03 molar. So we will calculate that now. And then we don't want to forget the negative out front, since it's a reactant disappearing, we see it with the negative slope. And so what we end up getting is that our rate is approximately 6.5 times 10 to the negative 4 molar per second. And just quick note, I actually forgot to do a 0 in my calculation, so it's actually 6.5 times 10 to the negative 5 molar per second. And so that's just good to know, and we'll see for the next slide why that's good to know. And then I also want to make sure that we're multiplying it by the negative, not putting the negative in front of that first concentration. And we know that reactions typically slow down over time, which we will then, see numerically on the next slide. So the key thing that I want you to know here is that you can take our curved lines and approximate the instantaneous rate by drawing a tangent line and finding the slope of that using the line that you've graphed. And note that, we're drawing it, we're approximating it. You might get a different number than me, but it will probably be in a similar ballpark. So when I did this calculation earlier, I picked 500 seconds and 800 seconds, and I got a value of 6.7 times 10 to the negative 4. Both of those are right. Both of those are my approximation, and it's pretty close. Okay, so for this one, we want to find the instantaneous rate of the disappearance of this chemical at 0 seconds and 300. So we can see here that they already did a graph for us. I'm going to pick for 0 seconds that point here. If you have a point that's on the line, on the tangent line, use it. And I'm also going to pick, no, not that point. Let's see, we'll just pick this point right here. We're going to say that, so for A, the rate of disappearance is going to be negative change in concentration of C4H9Cl over the change in time, and we're going to pick the time, so negative out front. The times that I chose were 0 and about like 210, so we're going to say 210 seconds minus 0 seconds, and the concentrations at 210 were 0.060 molar minus at the beginning it was 0.1 molar. All right, so then we'll do 0.06 minus 0.1 and divided by 210, and we'll make that the negative version, so we can say that the initial rate, so rate initial equals 1.9 times 10 to the negative 4 molar per second. All right, so we can see that that is faster than we saw at our point at 600. As a reminder, this point was 6.5 times 10 to the negative 5 molar per second. And now this one, the instantaneous rate is 1.9 times 10 to the negative 4 molar per second. All right, let's do it at 300. So we approximated it earlier. Let me draw that line again. Okay, so we have our line, and we're gonna pick a couple points on this line. I'm gonna do this in black so we can see our points. Let's zoom in. Let's actually use this point right here, which is at 300 seconds, and it's about 0.055. And then let's find another good point. You can pick any of the points on this line. I'm going to do 500 seconds and call it about 0.033. Okay, so what we'll do is we'll say that our rate for part B, oops, this is very big. Our rate for part B is equal to negative, the same thing, same equation, so we'll do negative. Our times that we picked were 500 seconds minus 300 seconds. And at 500 seconds, I'm approximating it to be 0.033 molar. And at 300, it looks like it's about 0.055 molar. All right, so when we calculate that, we're going to do 0.033 minus 0.055. And what we end up getting for this rate at 300 seconds is about 1.1 times 10 to the negative 4 molar per second. So it definitely, it was higher up here, lower here, and even lower at time 600. So it says, which of the following could be the instantaneous rate at time 1000? And notice that that's off the grid. So we're looking for anything smaller than what we've calculated so far. So 1 times 10 to the negative 4, that's basically up by that 300. 8 times 10 to the negative 5, that's bigger than at 600. 6.3 times 10 to the negative 5, that's really close to our 600. And so 2.7 times 10 to the negative 5, that's the only one that's small enough to be possible. So the last thing we're going to do on this section is talk about relative rates. We already talked about how we could measure the rate of a reaction following the reactants or products, but it would depend on which reactant and product. So rate does depend on stoichiometry. The reaction we had before, we had 1 mole of the chloral compound and 1 mole of the alcohol compound, and so we would get the same value. I could do that the rate equals negative change in C4H9Cl over the change in time, and that's also equal to the positive change in C4H9OH over the change in time. But when we have something that's not one-to-one, then we have to do something else. And a quick note that, we do need to change the sign because they have opposite signs. That's why we have a positive here and a negative here. And like I said, our rate of our reaction will always be a positive value. And that's why we put a negative for the rate of disappearance. So if we have a reaction that's not one-to-one, so we have something in general that's A of A plus B of B goes to C of C plus D of D, meaning that the coefficient is the lowercase letter and the uppercase letter is the chemical. So A and B are reactants, and C and D are products. What we're going to say then is the rate of the reaction is equal to negative 1 over A times the concentration of A over the concentration or the change in time. And that's the same thing for B, 1 over B times change in concentration of B over change in time. That will be the same as positive 1 over C, because C is a product, times change in concentration of C over change in time, or also plus 1 over D times the change in concentration of D over change in time. Meaning, if I had a reaction that had A goes to 2B, we would see that B appears 2 times as fast as A disappears. And so in order to make them evened out, we need to divide by 2, right? Because the rate of A disappearing is a value. B is going to be twice that. So to find the rate of the reaction, we're just going to divide B by 2 to kind of even it out and make it on the same playing field and give us the same value as it would be as if we measured A instead of B. So let's practice this now. We have this reaction where we have 2 ozone molecules go to 3 oxygen molecules. It says, how is the rate at which ozone disappears related to the rate at which oxygen appears in the reaction? So we have the rate of oxygen, or of ozone appearing, would be negative 1 over 2 times change in ozone over change in time. That's going to be the same as positive 1 over 3 times change in oxygen over change in time. And so those are how they are related. And they're both equal to the rate of the reaction. So it says if the rate at which oxygen appears, so that's something someone measured, and that's the change of oxygen over change of time, so it's literally this part. That number is 6 times 10 to the negative fifth molar per second at a certain point in time. They want to know what the rate of ozone disappearing at that time is. So we want to find the rate of ozone disappearing for ozone is going to be negative change in ozone over change in time. So this is what we want to find. And so we could take our equation up top here and get that by itself. So I'm just gonna copy that up top. And what we want to do is get this part all by itself, also with the negative, right? Because that means rate of disappearance. So in order to get that all by itself, you can see we need to multiply by 2 to both sides, and that's going to get rid of the half there. So then we can say that the rate at which ozone disappears, which is negative change in ozone over change in time, is equal to 2/3 the rate at which oxygen appears. And they told us that that has a value. They measured the value. The value at which ozone, or the oxygen, appears is 6.0 times 10 to the negative fifth molar per second. So we're just going to plug that number in. We're going to get 2/3 times 6.0 times 10 to the negative fifth molar per second. And that's going to equal 4.0 times 10 to the negative fifth molar per second. So basically, they're just telling us what we want to find is the rate of disappearance of oxygen, and we have a number for the rate of appearance. Where I see students get confused about is they think that that this is two separate things, like change in oxygen is one thing, change in time is another, but no, that literally is the definition of oxygen, the rate of oxygen disappearing. So don't separate them. They are one thing, and the change in oxygen over change of time is also one thing. Those are the slopes that we saw in the graphs earlier.